Hello everyone, my name is Chris Edwards, and today we are going to write a SQL query. Our problem today involves an interesting little twist on rankings. Now, to set the scene, let's imagine an American private school with a particularly nasty headmaster. At the end of each year, in flagrant violation of several academic privacy laws, the headmaster posts a public leaderboard of sorts, ranking all of the students in the school by their current grade point average, otherwise known as GPA. To further motivate and/or humiliate the students, the headmaster employs a peculiar ranking methodology. While some aspects of it are fairly standard, the best student is ranked number 1, the second best number 2, etc., something interesting happens when there is a GPA tie. Let's say 3 students have the third best GPA in the school. A more charitable system would give all of them rank number 3, skip ranks 4 and 5, and then proceed with rank 6 for the next lowest student. However, this headmaster is not charitable. In his opinion, if any of these 3 students truly deserved third place, they should have been good enough to beat the other 2 students. No. Instead of giving them rank number 3, the headmaster skips ranks 3 and 4, giving all 3 students rank number 5. And, in general, if multiple students share the same GPA, they are collectively given the lowest possible rank among them. This uncharitable headmaster happens to be preparing this year's rankings soon, and he needs a bit of help querying the student database. And that's where we come in. I'm going to go ahead and load up our database with a 15-row sample of the student data. There is a single table, grades, with 2 columns, a text column called student name and a numeric column called GPA. We need to write a query that returns the student names and GPAs from the grades table, along with a new column, student rank, that contains the student's GPA rank per the headmaster's uncharitable ranking system. The results should be sorted in order of highest GPA to lowest GPA. Just go ahead and run these setup scripts right now. All right. Now these are the expected results. As you can see, Kyle, the student with the highest GPA, has rank number 1. However, 2 students, Jonathan and Karen, have the second highest GPA, and so they both get rank number 3 due to the headmaster's uncharitable ranking system. The rankings continue consecutively for a bit until we get to what would be rank number 7. 3 students, Brittany, Ernest, and Rita, all have a 2.9 GPA, so we skip ranks 7 and 8, and they all get rank number 9. Something similar happens a bit further down, right here, with the 3 students who all get rank number 14. And that concludes the setup portion of this video. If you would like to have a crack at solving this problem yourself, there are links in the video description to all of this setup code and instructions on how to run it on your local machine. Feel free to pause the video now and come back later for a solution walkthrough coming right up. All right, welcome back everyone. We will now walk through how one might approach this problem. So the first thing that should jump out at you in the problem statement is the word rank. This should immediately make you think of the ranking functionality of window functions. Now, when dealing with problems involving ranking, there are 3 similar functions that you should consider. We've got row number, we have rank, and we have dense rank. So the first order of business is deciding which of these functions is most useful to our present situation. So let's take a little detour and remind ourselves of the differences between these functions by applying them to our current data set. I've prepared a query here that will be helpful in illustrating these differences right here. So we have here 3 different columns. The GPA row number demonstrates the functionality of the row number window function. GPA rank demonstrates the functionality of the rank window function, GPA dense rank, same thing for the dense rank function. And as you can see, the row number function always outputs a distinct value per row determined by the order by statement in the window definition. If there's a tie in the order, like you see here with these students, if there's a tie, row number just makes up a subordering at random, basically, to guarantee that each row gets a distinct value. In contrast, both rank and dense rank actually respect ties in the ordering and will give the same rank to all instances of a duplicated value. However, these two functions differ in what they do after a set of duplicate values. You can think of rank as keeping an internal counter every time it processes a set of duplicate values, and when the duplicates finally stop, rank continues on with the ranking value it would have used had the duplicates actually been distinct values. You can see here, the GPA rank column goes 1, 2, 2, 2 with the duplicate GPAs here. It repeats the rank 2 3 times in a row, but then it jumps to 5. The 2s repeat 3 times because 3 students had the same GPA, but the ranking continues on afterward to 5 as if we had actually been counting up the whole time in the background, 1, 2, 3, 4, 5. Now that's regular rank. Dense rank, on the other hand, will keep going after a series of duplicates with the next sequential rank number, regardless of how many duplicates appear. As you can see, for the very same rows, the dense rank values go 1, 2, 2, 2, 3. Because 3 comes after 2, it doesn't matter how many 2s there were before, dense rank will just move on to the next number in the ranking order. And a good way to remember this behavior difference just based on the function names is that when a lot of duplicates are present, the output of dense rank is in a very real sense much denser than the output for the regular rank function. With rank, you can get these big gaps in the values, like 2 jumping straight to 5, etc. But dense rank only ever outputs repeated or sequential numbers densely packed together. Now, with that reminder, which function is best suited to our problem today? Let's remind ourselves about the headmaster's ranking rules. First of all, in general, the student with the highest GPA should be ranked to number 1, the student with the second highest ranked number 2, and so on. But in the case of a tie, all tied students should receive the lowest possible rank among them. For example, if 3 students have the second highest GPA, then they all should get rank number 4, skipping over ranks 2 and 3. So off the bat, we can actually eliminate row number because the desired solution involves tied students sharing the same rank, and row number always outputs unique values for each row. The other important detail is that in the case of a tie, the headmaster expects a gap in the rankings. This eliminates dense rank, which never leaves gaps in rankings. So, by process of elimination, we are left with good old rank. So let's give rank a try and see how close that gets us out of the box. Taking into account that the headmaster wants the highest GPA to be ranked number 1, your first thought might be to order the ranking window by GPA descending. So let's give that a try. I have a query prepared that does classic rank over order by GPA descending, and let's see what that does for us. So that looks pretty close. There's one issue though. The ranking is too nice to the students who tied. It is giving them all the highest possible rank among them instead of the lowest. For example, right now the ranks go 1, 2, 2, 4, and the headmaster would really like them to read 1, 3, 3, 4. We need the ranking gaps to be shifted to appear between the duplicate values and the next higher value rather than between the duplicates and the next lower value like they are now. For now, let's take a step back and try to get a bit closer to that desired structure. Just to see what happens, let's try reversing the order of the ranking window. In other words, putting it back to a normal ascending rank. Note that I'm keeping the overall query order by clause the same, since this is the order that we'll eventually want for the final output. So let's try running this. And now this is an interesting result. As you can see, we actually made some progress in the structure of the rankings. The gaps now appear before the duplicates instead of after them. It starts with the highest GPA, rank number 15, then we skip rank 14, and then the tied students both receive rank 13. So this is great. The issue now is that the actual ranking values are wrong. Instead of ranking the best GPA as number 1, it's ranked number 15, in other words, dead last. Likewise, the worst GPA is ranked number 1. It's almost like the rankings are the opposite of what they should be and that we need to invert them somehow. But how can we do it? And in what world is 1 the inverse, quote unquote, of 15? Well, there are 2 ways to approach a problem like this, a practical way and a more mathy, theoretical way. Now, I don't want this video to get overly long or off topic, so I am mostly going to focus on the practical way that I would go about figuring out this solution, and then just mention a few details about the theoretical backing at the end, so as to provide the more curious among you with some ideas for further study. So fundamentally, we have one set of numbers, the correctly spaced but incorrectly labeled rankings that you see before you here, and we need to convert them into a different set of numbers, in other words, the correct rankings. We essentially just need to figure out the relationship between the numbers we have and the numbers we want, and then enshrine that relationship in SQL code. So let's just take a look at some of the numbers we have and compare them to the numbers we want them to be. So let's see, we have the first student, the student with the highest GPA, has rank number 15 right now. We'd like him to have rank number 1. The next 2 students both have the second highest rank. They're both currently ranked number 13. We'd really like them to have rank number 3, because the headmaster's uncharitable rating system, we'd skip rank 2 and just give them both rank number 3. This continues. The next person is currently ranked number 12. We'd like them to be ranked number 4. And this goes on, all the way to the bottom. The person with the worst GPA currently has rank number 1, and we'd like them to have rank number 15. So can you spot any interesting patterns here? Well, the first thing that jumps out at me is that as the numbers on the left go down, the numbers on the right go up. And having identified that general pattern, we can then ask ourselves to quantify this relationship. By how much are the numbers on the right going up as the numbers on the left go down? Now, it turns out these 2 sets of numbers are moving in perfect lockstep with each other in opposite directions. If the left number goes down by some number x, the right number goes up by precisely x every time. 15 goes down by 2 to 13, 1 goes up by 2 to 3, 3 goes up by 1 to 4, 13 goes down by 1 to 12, etc. And this relationship implies another interesting feature here. If every decrease on one side is matched by an increase on the other side with exactly the same magnitude, then the sum of the 2 numbers is always constant. And in fact, we can easily check that in every case here, the left number, the rank we have now, and the right number, the rank we would like to have, add up to 16. 15 plus 1 is 16. 13 plus 3 is 16. 12 plus 4 is 16. And so on. Now, how does that help us? Well, it gives us a formula. Specifically, left plus right equals 16. Now, what was our original goal? To find a way to calculate the correct rankings, i.e. the numbers on the right, given the current rankings, i.e. the numbers on the left. And now we have a formula relating the two, so with just a little bit of algebra, we can rearrange this formula to do exactly what we want. We just need to subtract the left number from both sides, and you get right equals 16 minus left. So now we just need to encode that in SQL and see what happens. And so yeah, if you remember, the number on the left here, that's the ranking we have now. That's just this. So this rank over order by GPA, that's what's producing these numbers. That's our left number here. So we just add a 16 minus on the front there, run it, see what it looks like. And that works. This produces exactly the rankings that the headmaster wanted. 1, preceded by 2 3s, skipping over rank number 2, goes to 4, so on, skips ranks 7 and 8, and gives all 3 of these students rank 9, and so on. This is exactly what we were hoping for. But we're not quite done. This solution works for this particular sample of student data, but would not work for most other data sets because we have this hard-coded magic number here, 16. We need to translate this literal number into a more generic concept that will scale to any data set. Now we must ask ourselves, what is significant about the number 16? Well, we are working with a data sample of 15 students, and 16 is just one more than that. So we need a way of writing something like the total number of rows in the table plus 1. We need a way of writing something like that. And so how can we get the total number of rows in the table? Well, one way would be to separately calculate a count star across the table in the CTE or a subquery or something, and then cross-join that back to our query here. But that's not the most idiomatic or straightforward way to do it. No, the easiest way to do it is we can just use another window function. We can just write count star over empty window plus 1. And leaving the window definition empty like that essentially defines the window to be the entire table, so every row in our results is able to reference an aggregation across the entire table instead of across some particular ordered sub-window of the table. Let's just run that. And yeah, we got the same results here. And that's it. That is a general solution that will work just as well with our 15 student sample as with the entire student body of the school, and our uncharitable headmaster will be very pleased indeed. Now, before I leave you, I want to briefly point you towards some concepts that will help explain why the formula we use to fix the ranking numbers works. Earlier, I posed the question, in what world is 1 the inverse of 15? And the answer to that is the world of modular arithmetic. Specifically, 1 is the additive inverse of 15 mod 16. And in general, what we were doing with our solution was converting each incorrect ranking into its additive inverse mod the total size of the table plus 1. If you have an academic background in computer science or mathematics, this concept may ring some bells. But if you don't, or even if you're just rusty, I recommend reading up a bit on modular arithmetic since it can really come in handy every now and again when working with code and data and the like. All right, well, that is it for this video. Thank you all for watching. If you have any further questions about this problem, or if you think of a different approach to the solution that I may not have considered, please let me know in the comments, and be sure to subscribe for more SQL query writing content in the future. Until next time, happy querying.